Hello, we are the Dimensionality Reduction sub-team as part of the Hack the Globe team for the 2025 C's term. My name is Advait Vinod Kumar,
My name is Marlon Wong.
My name is Daksh Mamnani.
and our project is called Drift ST, Dimensionality Reduction and Inference for Field-Based Surface Temperature. We worked with the data from the Globe Surface Temperature Protocol to explore how dimensionality reduction could help uncover outliers and improve data analysis.
Before starting the project, it is important to understand the data that we are working with. To simplify, GLOBE is an international program that collects environmental data from students and scientists around the world. It gives us access to real-world data sets such as the surface temperature records that we used.
Our dataset came from the surface temperature protocol, where students measure surface temperature using infrared thermometer. Each measurement includes metadata like date, time, instrument type, site latitude and longitude, and more. While the data had lots of information, it was messy, containing inconsistencies, missing values, and potential measurement errors.
This drove us to form a research question that addressed the problem. Which dimensionality reduction method best reveals structure in the surface temperature data and supports outlier detection? Dimensionality reduction is a technique to simplify large, complex datasets by projecting high-dimensional data into a lower number of dimensions while preserving as much meaningful structure as possible. It helps us make large datasets more understandable and interpretable. By finding the best method, we can uncover patterns and identify anomalies.
Before we can apply dimensionality reduction, we need to understand the structure of the data. So we start off with exploratory data analysis using tools like wide data profiling, which gave us a detailed overview of missing values and data types. Then we ran histograms, box plots, and kernel density plots to visualize distributions. Pairwise plots help to see relationships between numeric variables like surface temperature and elevation. Through this, we were able to remove columns with over 50% missing values, dropping null values, and adding useful metadata like season and country through quick reverse geocoding.
Then we applied the three most common dimensionality reduction techniques: PCA, UMAP, and TSNE. PCA was the starting point, which is basically a linear method that reduces the number of variables retaining the most variance. We then used UMAP and TSNE to capture more nonlinear relationships, giving us different views of the data structure. We also made a PCA lotus heat map to see which numerical features influence each component the most.
So, we needed a way to quantitatively evaluate which method performed best, and that's where we applied k-means clustering to each of the methods. We used three clustering metrics: silhouette score, Kalinske-Herabass index, and the Davies-Bouldin index. Across all three metrics, and as seen from the graphs, PCA outperformed UMAP and TSNE with a silhouette score of 0.45, a Kalinske-Herabass index of 7779, and a Davies-Bouldin score of 0.83. PCA was also found to have a very low reconstruction error of 0.035011, meaning it was able to compress the dataset to 12 dimensions while retaining almost all of the structure and relationships between variables.
We found that PCA best reveals structure in the surface temperature data, and so we moved forward using PCA as the basis for our outlier detection. We combined three unsupervised methods: isolation force, dbScan, and Gaussian mixture models to flag unusual data points. From the graph, we can see a total of 93 outlier points denoted by the points shaded in red. However, we did not have enough time to interpret these outlier points and possibly find any correlations between any variables.
This brings us to some of the challenges we had, which were time. We often spent a lot of effort exploring different methods and techniques that didn't always lead to useful results, which limited the time we had to analyze and interpret our complex findings. If we had more time, we would analyze the outliers more deeply, explore patterns more closely, and work towards integrating our findings with the work of other subteams.
Our results clearly showed that PCA provided the most well-separated and interpretable structure. Given its strong performance, low reconstruction error, and high speed, we recommend using PCA as the default dimensionality reduction method. For cases where local relationships matter more, a hybrid approach combining PCA with UMAP could be more useful in the future.
Thank you to Andrew, Brianna, Pramila, Ian, Dr. R, Sara, and Dr. C for making this experience possible. Much appreciation to the Hack the Globe team for their guidance and collaboration on the project. We've learned so much and are extremely grateful for this opportunity.
Getting hands-on experience while working alongside geospatial scientists on real-world environmental data through C's helped deepen my understanding.
C's made me appreciate the depth and creativity involved in data science.
Early in this internship, I was surprised by just how many directions our project could take with the vast dataset. But exploring those paths sparked a real passion for data wrangling and research in the field as a whole.
Thank you once again to NASA C's for making this opportunity possible.
And finally, our references.